Here, I'll just say the announcements in Portuguese and then come back. Bom dia a todos. Então, a gente vai dar início a mais uma palestra do Programa de Biologia Celular e Parasitologia. Quero avisar os alunos que a gente já tem estabelecido um formulário para as pessoas, para os alunos que atingirem as 15 palestras, para solicitar o crédito. Então, eu tenho mandado esse link do formulário nos avisos, nos convites. Vocês podem solicitar por lá e a gente vai passar para a secretaria depois de conferir a presença. Também queria avisar os participantes do curso que estão assistindo o simpósio completo, que somente as palestras, quer dizer, os alunos que estão matriculados no curso não vão poder requisitar o crédito para essas palestras, porque seria o crédito dobrado, né, pelo mesmo evento. Mas os alunos que não estão participando do curso, somente as palestras de quarta-feira que contam. Eu tenho recebido alguns e-mails com resumos de palestras de outros dias, mas as que contam para a nossa série de seminários são só as de quarta-feira. So I'd like to thank you a lot, Dr. Arturo, for accepting the invitation by Susanna and the Program of Cell Biology and Parasitology to be able to be here with us celebrating our 75th anniversary from the Institute. And I'd like to pass the word to Susanna, who's going to introduce you formally. Thank you again, and we'll start soon. Thank you, Susanna.
Thank you. First of all, I want to give the word for Bruno Diaz, the director of our institute, to open the session today. Please, Bruno.
Oh, and I'm sorry, I'm just saying one thing I forgot. If everybody else could turn off their videos once the talk starts, that will help with the streaming and with the connection. Thank you.
Bruno, você quer abrir ou vou direto eu?
Bruno is also our streaming guy. He's the one who makes sure that everything is going well to YouTube. So I guess he's speaking with that.
Just a second. I need to make sure that I'll get no microphone. So it's really a pleasure for the Biophysics Institute to host today Dr. Arturo Casadevall from Johns Hopkins School of Public Health that will talk to us about the fungal infection-mammalian selection hypothesis. And it will be really an eye-popping presentation for all of us. And I thank for everybody that is in the attendance today. And I'll give the floor to Dr. Baudelaire that will complete the presentation of Dr. Arturo now. Thank you very much.
Thanks, Bruno. But today, first I'd like to thank Professor Arturo Casadevall to accept our invitation. But Susanna is the person that will introduce him today. Please, Susanna, go ahead.
Good afternoon, everyone. Today we have the privilege of having Professor Arturo Casadevall with us for our graduate program in biophysics and for all our students and professors, and especially for me, this is a great honor. And so if we talk a little bit about Arturo, we can say that he received his MS, Ph.D. and M.D. from New York University and complete his internship or residency in internal medicine at the Lure Hospital. His infection diseases training was at Montefiore and Einstein in New York. He is actually a Bloomberg Distinguished Professor and Chair of the Molecular Microbiology and Immunology Department at Johns Hopkins School of Public Health. Previously, he served as Director of the Division on Infectious Diseases at Montefiore Medical Center and was a chair for the Department of Microbiology and Immunology at Albert Einstein College of Medicine. Nowadays, he's the author of over 900 papers, several books, and chapters. His major research interests are in fungal pathogenesis and the mechanism of antibody action. He's also interested in the problems with scientific enterprise, and with different collaborators show that misconduct accounts for the majority of retracted publications. He's editor-in-chief of MBio, deputy editor of the journal Clinical Investigation, and serves on several numbers of editorial boards. He serves on several NIH committees, including the NAS panel for review the FBI investigation of anthrax attacks, the NIS Federal Regulation and Reporting Committee at the National Science Advisory Board Biosecurity. He was a commissioner in the National Commission of Forensic Science and previously served as a president of the Medical Mycology Society of Americas. He is currently the chair of the Board of Governors of the American Academy of Microbiology. He has received numerous honors, including election of the American Society for Clinical Investigation, American Academy of Physicians, American Academy of Microbiology, Fellow of the American Academy for the Advance of Science, American Academy Arts of Science, and the National Academy of Medicine. Arturo, please, I hope you feel at home and be very welcome to the Carlos Chagas Filho Institute of Biophysics in the Federal University of Rio de Janeiro. I would like to thank you for you being here with us today, and thank you very, very much. And please delight us with your presentation. Thank you so much.
Susana, thank you for inviting me. It's a big honor for me to present to your group. A lot of my collaborators are in the audience. Brazil is a big part of my scientific world. A lot of people from Brazil have been in my lab and will continue to collaborate in many ways. And to me, that is one of the nicest part of my scientific career has been all the links with Brazil that go back many, at least 2 decades. So I understand that this is a very diverse audience. And so we're going to have a very different type of talk, not one that is going to be data heavy, but rather one that is going to try to be about thinking and I will begin with 3 questions that I had about 20 years ago. And these are just thought questions. Why are there so few fungal diseases for humans? Now you could say, what's the big deal there? Well, fungi are an enormous kingdom. And yet, we know that the dermatophytes, things like athlete's foot, are common, but most humans don't go around worrying about getting a fungal disease. Humans worry about bacteria like tuberculosis, viruses like COVID, parasites like malaria, but you don't hear them talking about worrying about fungi. So that's kind of interesting in itself. And then the next question is, why are mammals so resistant to fungal diseases? And in fact, they are very rare unless you have impaired immunity. But immunity cannot be the only answer because all vertebrates have adaptive immunity, but reptiles, amphibians are susceptible. So, a frog has B cells and T cells, and yet they are very susceptible to fungal diseases, as evident by the cataclysm that has happened to the amphibians with the chytrid fungus. And now we get into my own issues. So those are scientific things. These are personal issues. Why is medical mycology so unappreciated relative to bacteriology, parasitology, and mycology, virology? And the answer is simple. It has to do with the first 2 questions. Since you have fewer diseases, people treat fungal diseases as less important. So my approach to these questions has been to read, and to read outside your field, to think about the big picture in terms of evolution, mammalian selection. And when you read into this, you realize that there is a voluminous literature in evolution, but nobody thinks about infection as a major driver of evolution. For example, none of the mammalian emergent hypotheses have considered evolution, and there is really no good explanation why mammals become the dominant large animals. To again think in terms of deep time is thinking in terms of millions of years. To embrace holism, to succeed in science, we have to be reductionist, and you have to go deep. But there is a problem. If you go too deep, you can get into a hole. And you got to be able to think outside of your own area and to try to find an exploratory synthesis that one can fill the details in later. So give you an example of reading outside my area. Here is a paper that I remember when I read it that influenced me a bit. This is the platypus. The platypus is a primitive mammal that lays eggs, but it has a much lower temperature than we do, as of 32 degrees. And here you see that it's susceptible to a fungus that we are not susceptible with, because the fungus only grows to 36 degrees. And that began to think about the possibility that there was a relationship between those questions that I posed to you, that maybe the fact that we are resistant to fungi would have to do with our temperature and other things. So that began to think about the age of mammals. So the age of mammals begins after the KT event. And I'll tell you more about what that is. That's the cataclysm at the end of the Cretaceous. And what the big difference is that you see this big replacement on the reptilian megafauna by the mammalian megafauna. Today, in most places of the world, if you go outside and you see animals, the animals happen to be birds or mammals. And they're both warm. You don't see large reptiles because they simply did not do well in the world that followed the Cretaceous. So these are dinosaur extinction theories that I found on the web. Some of them are funny, otherwise are scientifically real. Obviously, I don't think smoking had anything to do with them. And I don't think that the reptiles and the mammals engage in battles at sea. I also don't know what to make of the biblical story. Oh crap, was that the day in which the dinosaurs just missed the Noah's Ark? If people used to think that it was the small mammals that ate the eggs, that makes no sense at all. But there are at least three major scientific theories. One of them got published in Current Biology, arguing that the dinosaurs could have caused climate change by passing methane gas. I don't believe that for a minute. I think the two real viable ones are volcanism and a rock from outer space. And these two were happening roughly at the same time. And volcanism could have contributed to degrading their environment, such that when the meteor hit, it basically resulted in a final catastrophe. But there are many theories for the dinosaur, but what I'm really interested in is how come there wasn't a second reptilian age? We have reptiles today. Why didn't they just take over the world? Again, after all, reptiles are more fit than mammals in many ways. They need 1/10 the energy. They reproduce much faster than we do, and some of them do care for their babies, but generally mammals spend a lot more energy also in the next generation. So to me, this replacement didn't make a lot of sense, because I would have imagined that the reptiles would have then, the survivors which have rapidly recolonized the post-KT boundary world and given us a second reptilian age. Here is the cost of the mammal lifestyle. It is very expensive. Here you are. This is a log plot. So you are at the very top of that curve, which means that you need many orders of magnitude more energy to make it through the day relative to a frog, relative to many of the other organisms. Having a high energy is very expensive. We have to eat a lot. Most of us have 3 to 4 meals a day. I mean, think about the enormous amount of calories that is needed to maintain the mammal lifestyle. They were a very minor group until 65 million years ago. And then you had the great mammalian radiation after the KT event. And what I want to know is how this unfavorable lifestyle became dominant. And the explanation obviously had to be in the distant past. So let's go back to the Cretaceous world. The Cretaceous world was a warm, volcanic, and forested planet. There were forests in Antarctica. The Atlantic was tiny. The currents and the weather there would have been very different than it is today. And then it was populated by this reptilian megafauna, and then the asteroid hit in the Yucatan. And you can, if you go to the Yucatan today, you can go see the cenotes. People go see the cenotes because that's supposed to be where the Mayans did the sacrifices. No, next time you go to Mexico and you go to that area, go see the cenotes because they are a geological formation that is found only in that place because they are the rim of the crater. So the limestone melted and then rapidly solidified and created channels that go into the Gulf of Mexico. The post-impact world was a hellish place. You had fires, smoke and dust. There was no sunlight for at least 6 months. Some estimates are that there was no photosynthesis for 10 years. Global temperatures dropped by 10 to 15 degrees overnight. So you can imagine the enormous stress that was put on this ecosystem. And there is evidence of massive fungal proliferation at the KT boundary. This has now been very well documented in that you can find this layer of just spores after the catastrophe. And these spores, any animal living in those conditions would have been exposed to large numbers of spores. And you know that even if with low pathogenicity organisms, if you give enough of an inoculum, you can overcome immunity. And these survivors would have been highly stressed. So I have argued that endothermy, being warm, provided this resistance to fungal diseases by creating a fungal barrier. This is me drawing stuff. So the post-impact world, the reptilian megafauna is killed by the blast, the disruption of food sources, the chilling of the planet. Reptiles fight off fungal infections, but there was no sun. Reptilian eggs are susceptible to fungal diseases. In fact, you can find fungi in dinosaur eggs. So this was, obviously, there were fungal pathogens back on the Cretaceous. And these would have been around to harm animals that were at risk. So, but we know that some small animals also survive. So if the reptiles were so fit, I ask again, how come we didn't have a second reptilian age? So I was thinking about all these things, and I went to give a talk at Miami University in Ohio. And Nicholas Money, who was then the editor of Fungal Genetics and Biology, I remember that I just, in the middle of my seminar, talked about this without a lot of, like the ideas that come up in the seminar. And he said to me, write them down. So I went back home and I wrote this paper. And this paper, I remember, got featured by the regular newspapers, and it was a lot of fun to write. And so that was about 15 years ago. And the main point was that a fungal filter selected of mammals over reptiles. So you have the calamity. Here is the age of the reptiles. Here is the boundary. And here is the age of mammals on top. So you have this catastrophe. You have deforestation, this warm planet. All those forests come down, and the fungi, as you know, are the great degraders. You have massive proliferation, and that would have selected for the age of mammals. So for the next 15 years, you work to shore up the hypothesis. This is the kind of science that you don't have to worry about writing grants. You're not going to write a grant about this. The way you do it is you keep thinking about it. So my goal was to find example and experiments of nature that supported temperature and fungal susceptibility notion. To obtain experimental data where available, and I'll show you some examples. To keep up with the geological stories of the KT event and incorporate information into the hypothesis. What this means is reading what's going on in the geology literature. And the beauty is that the hypothesis opens up a lot of new ideas and possibilities, including in the era of global warming. So then, a year after this happened, began the white nose syndrome in North America. And this provides important indirect support. So in North America in 2006, a disease began that affected bats. The bats are healthy in the summer, but in the winter, their temperature drops to 10 to 12 degrees, and they become susceptible to a fungus. It's going through various names, but the original name was Ichthyomyces. And what happens is it grows in them, and this is hypha, so you're in the nose, it appears to be like a white nose syndrome. So that suggests that, gee, there must be something to temperature and resistant to fungi. And that was supported by the fact that if you take those bats and you bring them into a laboratory and you feed them, just getting their temperature up will clear the infection. Then I worked with Vincent Robert to see if we can get additional data. So Vincent Robert is associated with the CBS collection in the Netherlands. And I ran into him and I said, do you guys record the maximal temperature of your isolate? He said, sure, we do a temperature study. So what he did was he looked at 4,000 fungal species, and you can see that they replicate pretty well to about 25, 30 degrees. And then after that, the majority of fungal species don't do well. In fact, by the time you get to 40 degrees, you're down to about 25%, 41, 42, you're less than that. So he took that. So then I had a conversation with Aviv Bergman, who's a mathematician. And what he did was he took that data and he took the cost of being hot, which is a well-known equation in physiology. And he asked, what is the maximum? What is the maximum by which you can protect against fungi without having to eat all the time? And the temperature that comes up is 37 degrees. Now, that could have been a coincidence, but it wasn't 28 degrees and it wasn't 48 degrees. Again, a piece of data that fits in nicely with the synthesis that I'm trying to develop. So birds are also resistant to fungal diseases. In fact, they are susceptible primarily to Aspergillus, which is the only fungus that really grows into the 40s centigrade. And primitive animals were susceptible, so all the pieces are fitting in. So then I did the first update in 2012, and you can see it down there. And if you want to notice that I took the word dinosaur out of the title because people get confused. They thought Arturo's talking that the fungi killed the dinosaurs. No, the dinosaurs died because of the calamity. What the fungi did is they kept down the reptiles so that we had the rise of mammals. So I gave this prestigious talk at the National Institute of Health, and they had an artist that they did this drawing for me. And you can see the reptilian megafauna goes through a fungal filter, and then you have at the other end the mammalian megafauna. So we began to look for other pieces of data. Can you show that there were pathogenic fungi at the Cretaceous? Well, you go back. So I work primarily, as many of you know, with Cryptococcus neoformans. And during this time, a lot of information is beginning to appear about when this species, when this strain speciated, and there was apparent that the ancestor of the Cryptococcus had been somewhere in Africa, and that the breakup of Gondwana was about 100 million years ago. So Gaddii is thought to have come from Brazil. And the neoformans are from the ancestors from Africa. So we propose that a continental drift had led to the separation of these two species. So, and now, since both species are pathogenic today, and they separated 80 to 100 million years ago, it stands to reason that the pathogenic traits that they have today existed 100 million years ago, such as the capsule, melanin, and other things like that. And one of the nice ways of thinking like this is that other people who know a lot more about this than I do took the idea and did very well. Because one of the mysteries in the field had been why, for example, are the isolates from Spain so close to the isolates of Asia? And if you superimpose the isolates over the map of Pangaea, you can see that these isolates from Spain are a lot closer to Asia than some of the other isolates from the world. So it gives you an idea that when you begin thinking this way, a lot of things opened up that you can now make links with. Then we looked at carefully looked at pathogenesis of Cryptococcus. So we took strains that we knew were very far away in evolution. 65, 100 million years ago had separated. And then we studied them in macrophages. And what we found was that they use the same pathogenic strategy. So what it's telling you is that these ways in which these strains cause disease are ancient. And they were back then during the Cretaceous. So these things are conserved, we think, is because they are maintained for survival in amoeba. But it also tells you that in the Cretaceous, there would have been fungal pathogens. So then last fall, I've been invited to be part of the CFAR. The CFAR is a Canadian research organization. And for the first time, they are supporting mycology research. Leah Cowan and Joe Heidman are involved. And they asked me to be part of the advisory group. So I flew to Toronto, and because a lot of people like me to present this story because it's like an easy way to get into a meeting. So they say, Arturo, why don't you come and tell us what you think about the mammals and that kind of stuff. So I gave, this talk, and I gave it short. I think it was 20 minutes. And then Chris Damon from the Gates Foundation, I went to get coffee, and he said to me, what about food? Could mushrooms have provided food? And then we began to think about all the implications of temperature for digestion of mammals, and realized that there was a lot of information that could be used to update the hypothesis that fit in very nicely. So it turns out that both mammals and reptiles could have eaten mushrooms for food. But reptiles have a problem. Reptiles can swallow and cannot digest unless they're warm. It's because their digestive system requires temperature. Whereas the mammals would have been hot, so they would have had no problem to digest the food. The reptiles also cannot move because it's cold, whereas the mammals could go around looking for food. And then we looked more into the literature and found out that reptile sex ratios are greatly affected by temperature. So reptiles that managed to replicate during this time would have had another problem in that their ratios of males and females would have been altered, resulting in more problems for replication. Whereas mammalian worms would have allowed movement, food foraging. Mammals have no problem. You have no problem digesting food, even though it's cold in Rio de Janeiro these days, because your temperature allows the process to go on. So you can see how all these things could have contributed to giving the mammals an advantage. And in those terrible days after the calamity, a difference in replication would have led to an increase in mammals over reptiles. So those mammals then become the founder species and begin down to compete with the reptiles, simply by the numbers. So the post-Kate event, the weather conditions greatly favor mammals apart from problems with fungal diseases. So now you have fungal diseases, and you have basically the ability to much better survive the calamity because these are worms. So this was the second update that was published last month. And this time I got an artist, because I can't do anything like this, to draw it up for us. And they did an amazing job. So here you have the asteroid, and the asteroid hits the world and causes tremendous damage. There are tsunamis that are several kilometers high, sweeping through North America. There is the shock wave. You have fires, rotting wood on fire because the ground is kicked into low orbit and then re-enters as flaming meteorites. And then you have a very long night because there is too much dust and too much smoke in the atmosphere. There is no sun. Then you have the decline of the ectotherms, and then you have the fungal bloom. The ancestral mammals are selected, and because they get an advantage, then they now disseminate. So it becomes to be internally consistent. Mammals don't get fungal diseases because they were selected by fungal diseases. And you can begin to see how all the pieces fall into the story. So it also leads to thinking in other ways. So the world is getting warmer. What's going to happen to infectious diseases? Well, people are worrying about mosquitoes and things like that. But there is something else going on. If you look at most of the endemic mycoses occurred in tropical and subtropical regions. Why? Because if you are in a warm climate, statistically, you are more likely to have adapted to a temperature that can defeat human defenses. But as the world gets warmer, all the fungi are being put under selection pressure. Could they adapt rapidly? Well, there has an experiment has been done and published, and that's this paper down here, directed evolution of a filamentous fungus for thermotolerance, that is very worrying. This is a fungus that kills insects. And what the problem is that the insects are smart. They will, when they get the fungus, they find a warm rock and they sun themselves and they kill the fungus. So the company adapted the fungus to grow at 37 degrees over a period of 6 months. That shows you how rapidly these things can adapt. And I think it's a scary experiment, because if you have all the necessary genes for defeating an insect, and now you basically acquire temperature resistance, well, it may allow it to be a pathogen for mammals. So we propose that global warming will bring new fungal diseases for mammals that are currently unknown. And then we talked about Candida auris. Candida auris is a new pathogen that was not known to medicine prior to 2009. And in 2011, 2012, emerged simultaneously in 3 continents. And the isolates are not related. In India, Venezuela, I'm trying to think the other place that it emerged. But it wasn't, I don't believe it was the United States. In North America, it was Europe. Oh, I'm sorry, it was South Africa. It was in South Africa. So the isolates from South Africa, Venezuela, and India are not related. This was not spread by a patient moving from one place to the other. So we have in fact found evidence that the fungi are adapting. This is a very messy data, but what this is, the data, that collection in the Netherlands, they record the maximal temperature of all isolates when first deposited. So the Ascomyces, which is a group of the fungi, are already adapted. So forget about the top 2 lines. The Basidiomyces, you can see that the trends are upward. So these organisms were already responding to climate change before we knew about climate change. And Candida auris may be the first example of a fungal species becoming pathogenic by breaking through the mammalian thermal barrier. It is resistant to most antifungal drugs. It was not known to medicine prior to 2007. Emerged simultaneously in 3 continents that are very different. The only common denominator is that all these places are experiencing warmer climates. And these isolates are genetically very distant. So we proposed last year in a paper that got a tremendous amount of attention that this was the first example of a fungus adapting to warmer temperatures and then defeating our thermal defenses. So to end, here are the twin pillars of resistance to fungal diseases. This is why you don't worry about the fungi and you worry about COVID and you worry about TB and you worry about malaria. If you have advanced immunity and we are hot, advanced immunity can be defeated by AIDS, cancer, and drugs, and that's why mycotic diseases are associated with immunocompromise. But you could defeat your thermal barrier if the fungal adapts to survive around 37 degrees. But one of our concern is that there are many fungal species out there that are already loaded with virulence factors, but they cannot harm mammals because they cannot grow at mammalian temperatures. If you adapt them, then we're unfortunately could be seeing the emergence of a lot of new fungal pathogens, many of which are resistant to all known antifungal drugs. So I want to point out two other interesting things. This was a paper that appeared last year or the year before, showing that human temperatures are dropping since the Industrial Revolution, and they're dropping by about 0.3 degrees per birth decade. So people born this decade are going to be a lot cooler than people born in the past. And the speculation is a result that we're living cleaner lives. If you had lived in the past, you would have been infected with tuberculosis, parasites, etc., and there would have been a lot more inflammation. And inflammation generates heat. So the estimates is that we are about 0.3 degrees cooler than people who were born 100 years ago. And you might say that's a small difference, but there are a lot of fungi out there. And a small difference like this could allow an organism with a temperature tolerance of about 37 to 38 degrees to establish itself in a human host. So we having another problem in that our thermal barriers are not what they used to. People ask me about fever, and let's take a look at fever from the lens of FIMS. So every good theory needs to have an acronym, and this didn't have an acronym. So I made one up called fungal infection mammalian selection, so that it can have an acronym. So fever is a natural immune response to infection, and mammals mount fevers by driving catabolic process to their cells that increase body temperature. Ectothermic organisms, such as insects, they do what are called behavioral fevers. They beat their wings. Reptiles try to find places where they can sun themselves. And in experimental system, the role of fever has been shown to be very important in host defense. But in medicine, in humans, it's been very hard to show a role for fever. In fact, the first thing that doctors do when you have a fever is they give you an antipyretic. You know, when I was a doctor, when I was practicing, the first thing you write when people get admitted is acetaminophen if they have a fever. It's a standing order. And the question is, why is it so hard to show that fever is important for humans? Well, think about it. Almost all our pathogens today are acquired from other humans. COVID is acquired from another human. So they are already coming to you thermally adapted. But if you were alone, if you were living in a rural area, the majority of potential pathogens that you will run to will be environmental organisms. You cut yourself, you ran into a plant and you got a spine put into you. So you scrape yourself. And for those organisms, raising the temperature 2 degrees could provide tremendous protection, because those organisms in the environment are generally temperature adapted to the environment. Very few of them can grow at body temperatures. So this way of thinking allowed me to propose that thermal restriction is an antimicrobial function of fever. And it's interesting that nobody had really thought about this, but you had to be thinking in this context to put it together. 2 to 3 degrees is a huge deal if you got dirt in a wound, because most of those organisms in the dirt are simply not going to be able to survive in mammalian temperatures. So this is my last slide, and this is more to talk about how to do science. And there are a lot of ways to do science. And what I want to say is that all ways are good, and we need them all. And you need to find how you're comfortable. But you know, many people take data and then use it to generate thought and to do theory. Others take data, have a theory, and then they go to thought. You could go from theory to thought to data, theory to data to thought. What you see here is that I begin with thought, and then you take it to theory, and then you get the data. In other words, you begin with thought, and you go to data and to theory. And science should be fun. I went into science because I loved its capacity to explain to me my world. Now, a life in science is hard. you got to deal with reviewers, rejected manuscript, rejected grants, people telling you your work, whatever. But the important thing is that you have the capacity to think. And one should not be afraid to think or to take risks. Thinking does not require any grant money. It requires your ability to put things together. And this is no different than exercising. The more you kind of look around and you try to make connections, the more connections you make. So what I urge all of you, and in particular the students, is to think and not be afraid to take risks. That if you're wrong, you can always revise it. You can always amend it. And these are examples of some of the papers that we have published over the past year that, there are no grants that are going to get written on this. But this is why I went into science, because I am interested in the explanatory power of thought and putting it together in many ways. And as long as I'm around, I will continue to try to work. For example, I'm trying to establish a collaboration with some people who work at the KD boundary, because the next step may be to look at spores, fungal spores, and see a portion of them come from taxa that have been associated with virulence. And that could be a very fun project to do. It will not prove any of this. By the way, you cannot prove these ideas. You can only disprove. But you can continue to get supportive evidence. And even if the ideas are not correct, they lead to other things, as I pointed out to you, that in a way lead to a much greater, much richer scientific thought. So I know that many of the audience are in very different fields. I urge you to think about, make different connections. One of the best ways to start is by reading outside your field. People say, how do you do it? Do you have time? I said, I don't have any time. But I give you an example. A month ago, for example, 3 countries sent spacecraft to Mars. And one of the things I did was to look at the scientific instruments in them and to ask, how would they make the measurements? What kind of measurements would they make? How would the data be interpreted? And you begin to make connections that you would not ordinarily do. So when I try to read science, I try to read science outside of my field while keeping my field very much in my mind and to try to make connections with it. So with that, I'm going to end. And I think that if I get out of this, I can see you guys again.
Thank you, Arturo. Thank you very much for your excellent talk. And we have questions from YouTube and from Google Meets for our student and professor. Are you ready to answer all of them?
I'm ready. You gave me 40 minutes. I did it in 43.
Great.
But I was after the introduction.
It's not my fault that you have this excellent CV. So I need like 15 minutes to talk about you. So the first question came from one student, Mariana Lucy. She was thinking about temperature and survival of different fungi. She said that you talk about temperature is a stop for fungal infection. So can you explain a little bit how, for example, Sporotris shanki could survive in cats easily at temperatures around 39, 40,000 degrees?
So if you look at the fungi, the fungi range in thermal tolerance up to organisms that are in the 40s. The aspergillus can grow to 44, 45 degrees. In fact, you find them in compost. So I'm not surprised that Sporothrix can grow at higher temperatures. Growth in higher temperatures is a necessary but not sufficient condition to cause virulence. I would point out to you that Sporothrix, the majority of Sporothrix infections are cutaneous, and the temperature on the skin is much cooler than the core, as many as 5 to 6 degrees centigrade. So it's, there are plenty of fungi that can grow at higher temperatures, but they can't cause disease, because you need to have two things. You need to have the capacity to grow at higher temperature, and you need to have the virulence factors to defeat the immune system.
Okay. Rodrigo Figueiredo from YouTube asked, but why so few fungi explore the mammalian environment? I mean, is there a limitation to fungi as a consequence of fungal biology? Things are war?
I think that people often say, well, why haven't the fungi adapted to cause disease? And that's not the right way to look at it. The way to look at it is the fungi as a biological kingdom are largely involved in degrading matter. Their big ecosystem is as degraders of plant matter. The mammalian world offers them very little. They don't need a mammal to replicate. They don't need a mammal for transport. All they often need is wind to move. So this idea that there will be some desire for the fungi to adapt, it doesn't quite make any sense to me. I think what happens is that you have fungi with a big distribution of temperatures, and you have some that can grow above 37 degrees, and only a fraction of those happen to have the virulence factors. And that's why we have so few pathogens in mammals.
I think people get scared when you said that non-steroidal anti-inflammatory drugs like aspirin, ibuprofen could make mammalian more susceptible to fungal infection. Because you go to the hospital. I don't think it would
make them more susceptible. I think that the question is, why do we lower temperature when you have a fever? Why do you take? And the reason is because you feel better, because people with fevers don't feel very well. But it's also important to realize that if you happen to work, that fever puts a tremendous stress on an organism. And those of you who work in labs try to grow an organism at a higher temperature. So it's interesting that we defeat one of our innate mechanisms of protection. When we get infected, the first thing we do is we take aspirin or we take acetaminophen.
Anamelia Boca, I think you know her.
Hi, Anamelia.
Anamelia is in YouTube, I think.
I don't see her, but she must be one of the squares.
Yes, she is in the YouTube connection.
Okay.
Of course, she said that you give a great talk.
Thank you, Anamelia.
The question for her is, how did geologists, archaeologists, astrophysicians, and other researchers outside the health and life science reacted to your theory through the years?
So I think the best explanation is bewilderment. They don't know our field, so they look at it and they say, it's been the reaction. I've been engaging with them. I had one person who wrote to me who said that they would not believe this unless you can find a fossil of a dinosaur with a fungal disease. And I said, that's crazy, because you would have to find an organism that died in that boundary. And that's just going to be very hard to find. I think people are amused. And you know what? That's all right. They don't have to agree. So far in 15 years, I haven't had anybody come and say to me, your ideas are wrong because of this, this, and that. And I consider that a victory, how complex all of this is.
So I make a conflict here. The last question was from Andre Nicola. The Anamelia Boca question was, do you think the innate immunity improvement could be one way to increase our immunity, innate immunity training?
Yes, but realize that any increases in immunity come at a cost. Look at the patients who are dying of COVID today. Mm-hmm. They're dying from the immune system. They are not dying from the virus. And everything has a cost. I think that I'm sure that you can, if you can rev up innate immunity, you can keep away all these organisms. But In more innate immunity, you're going to have more inflammation. And who knows what that will do. And that will be followed by scar tissue.
Our professor, Norton Hayes, he said, in the damage response framework of microbial pathogenesis that we use a lot for our classes, host, houses, and associated microbes interact with other microbes such the outcome results in damage, benefit, or indifference. Does the fungal infection related immune reconstitution syndrome could be related to human temperature dropping?
You know, I think, I'm not sure we can make that conclusion because the human temperature drop is so small. I think that, and it's measured over a population. But I think the worry is that when, look, 100 years is nothing in evolutionary time. But if we keep dropping the way we are, we're probably going to be a degree cooler by the end of the century. And then we may have additional problems. At least, you know what? At least we'll need less food. There's probably going to be people put on weight if they're cooler.
Professor Julius Scharfstein from our institute, he wants to ask you a question, but I would like him to ask you the question.
Hi, Julio.
Oh, very stimulating talk. Thank you so much. The first question has to do with what would be the impact of a drop in temperature, as you have so nicely described, in the cascade activations? Because, I mean, for example, complement, right? So I assume that complement should have a role in the defense against some fungal infections. And I would predict that because you need catalysis and you need sequential activation of so many substrates in order to have an optimal opsonization, that probably you would have an impact if you compare the range of temperatures 100 years ago vis-a-vis the temperatures that we have in our bodies. The second question has no relationship to my perception with temperature, but it's very intriguing to me because the issue of alpha galactose synthesis in primates, because we lost the alpha galactosidase gene, and as a consequence, we are not tolerant, so we have very high levels of anti-gal. I would like to know what is your feeling. Is this a second level of natural protection that primates have as compared to lower vertebrates that, of course, do not develop that kind of response?
That's a very interesting idea. And, you know, what I would encourage you to do is to think about it and write it up. I don't know the answer to it, but it is very interesting to see where that was lost in evolution, try to imagine what the events were at that time. The first, so I don't have an answer for the second one. My suggestion to you is write it up. Figure out a way to get it out there that anybody can find it in PubMed. Don't worry about the impact factor.
No, I'm not worried.
Worry about that I can find it so I can cite it.
I was just inspired by your talk.
But the first part of your question is actually very important. And you're basically saying, look, you're going to have different biological processes going on at different temperatures. One of the things that we don't address in immunology or physiology is that the different parts of our body are already at big temperatures. My hand here is probably around 33, 34 centigrade. Inside my body is 37 to 38. And so I think built into immunity and built into physiology is a lot of temperature redundancy. But all immunology work is done at 37 degrees. And I urge people to often explore, for example, macrophage function and things like that at lower temperatures. Because if you get a cut in a finger, all the reactions there are happening 30, 31, 32 degrees. And that is probably very different, cytokine release, complement activation, things like that, than it happens in core temperatures.
Yeah, measuring the level of C3b deposition, for example, in a fungi in different temperatures, it should be a very straightforward exam.
Julio, to my knowledge, it's never been done.
Incredible. Yeah.
It's never been done because you can imagine you try to write it up and people say, why are you doing that? The temperature is 37 and people are not thinking that the hands are really where you want complements. When you get a paper cut.
This is surprising because you should expect that during fever, you should have an increase of sonization, which would make a lot of sense, So
right.
It's a very fundamental question. It would be very surprising that people have never done it.
I have never seen any immunologist done at 37 degrees. Very rarely do you see any immunology outside of 37 degrees. But I think it's it's an unexplored area. And if I had enough years, I would do a lot more work cooler, because another way to think about fever is, maybe the reason for fever is that when you have a fever and you have a cut in your hand, you at least raise the temperature in your hand closer to your body core. So good question.
Professor Bruno has a question. Please feel free to ask the question directly.
All right. Thank you very much for this wonderful talk. I first would like to apologize for fumbling the presentation of Dr. Arturo, but I was caught a little bit off guard and I haven't really prepared anything. We had just talked before very informally, and I completely forgot about the whole presentation bit. And Dr. Susanna was obviously very well prepared for this presentation and did the honors for the Institute of Biophysics. I really hope to have redeemed myself with this apology. If not, I just have to go back and edit out this part of the video. So the register will be okay.
Bruno, don't give it another thought. The important thing here, the one thing I wanted to make the point is science should be fun.
Yeah.
And one shouldn't be afraid to think and make connections. And just keep your other work going.
Sure. No,
it gives you funding. And it's a lot of fun to do this. And I think that we should do more of it in every field. Right.
No. It's a definite, very elegant hypothesis that explains the needs and the importance of the cataclysmic event, but it's not enough. But at this point, you already had the fungi there, and the change in the weather increased the number of the fungi and actually hindered the response to them, as ectotherms would not mount a fever response if they don't have the external source of heat. So it's very interesting. It's very nice. But I have one very naive question. The surviving reptiles would not be selected for a more effective antifungal response, and if it's not, how do you reconcile, or if there is any need of actually reconciling this situation?
So there could be it could be that the survivors not only had higher temperature but also got selected for a bigger response. It could also be that the reptiles that we have today, the iguanas and things like that made it, was because they had more capacity to survive the cataclysm. We don't know, obviously, about the ones that didn't make it, but we do know that for whatever reason, the mammals took over, and took over despite all this energy cost. And I think that there is a lot of work that could be done looking at comparative immunology. I can't do it because I don't have any time or bandwidth. But if you begin to think this way, to look at for traces of a selection event in the genomes.
Right. Thank you very much.
All right.
Arturo, can you stay with us a little bit more? There is
I have another thing coming up. How long? Maybe a couple of minutes.
Okay, so I have a question that is more or less the same for everybody. With climate change and how this affects interrelationship species and different ecological relationship between organism and human host, do you think that new species can appear like a new infection diseases, like a new fungi that can affect humans?
I think so. I think that, the majority of the fungal kingdom and bacteria, by the way, this applies across the board. And this would apply to viruses too. For example, if you have a virus of an iguana and the iguana gets used to living at much higher temperature, that virus has to replicate at much higher temperatures too. So I think that this is general to microbes. Most of the microbial world is unknown. Most of the fungal world is unknown. So I think that the danger, obviously something like Candida auris, is that some of these organisms that will emerge simply by temperature selection. People say, by the way, here is an important clarification. People say, oh, how can this be? The global average temperature of the world is only maybe 1 or 2 degrees. I think that's not the right way to think about it. The right way to think about it is think about it in terms of number of hot days. Every single really hot day is a selection event.
Okay.
So if you go from 10 very hot days a year to 100 hot days a year, you're just going to put more pressure on whatever organisms are there.
So if I have to ask you all the questions that we have in the list, I'm going to be here until tomorrow because your work is excellent and people has a lot of questions regarding your theory. And you don't talk about melanin and Mars. If you talk about melanin and Mars, we can stay until Friday from next week.
I'm sorry, but I
know.
Actually,
we are so happy to be with us.
And it's wonderful to visit.
You can be in Rio de Janeiro wherever you want. You know that.
Especially over Google meetings, right?
Yes. And in person too. I think for us will be a pleasure if one day, maybe soon, you can stay in our institute. And now I'm going to pass the word for Miriam Bernanke, that is the organization for all this event.
Hello. So I would like to thank you again, Dr. Arturo, and for your time here with us. I think it was an amazing talk and gave us a perspective, at least for those of us who haven't thought much about it, an amazing perspective. I had a question, but I'll leave it. I'll email you, so I won't keep you. Sure. And I don't think I can use the leverage I have here.
Yeah, well, I'm slow in answering my emails this day because I'm very much involved with the plasma store in the United States.
Oh, sure.
Sure. My name has been all over the news, and I'm actually afraid to get off because I have an hour and a half of emails that have arrived, and who knows what disaster came in when I was visiting you guys in Rio.
It's what we said. The worst thing of taking a vacation is coming back from the vacation. And that is, yeah. So, thank you very much. And I think it is a pleasure. And thank you the program as well, the cell biology and parasitology program for giving us the opportunity of having you here, and Susanna especially for inviting you. So I'll tell the students we're back here next Wednesday, and the symposium will go on. There is a talk tomorrow and the day after, but in this series we're back on next week. And so thank you very much, and thank everybody for being here with us.
Thank you. And
thank you.
And goodbye to everyone. Bye-bye, and thank you for having me.
Thank you very much, Arturo. Ciao. Pueden cortar.